Welcome to the notebook for Module 3. In this notebook, we're going to talk about quantization and how we can apply it to our functions and to our deep learning architectures so that we can save space both for training and at inference time. Quantization is the approach that takes a full representation of a high precision number and downgrades that to a lower resolution representation of that same number. We'll walk through step by step from a single value all the way up to a trained neural network on how quantization works. As always, we need to make sure that our compute resource is running in our notebook, and we'll start, as we always need to do, by running the classroom setup script. Now that that's done, let's install all of the Python libraries that we'll need to use during this notebook. We'll be writing PyTorch code from scratch, so we'll need to include all of the right libraries from PyTorch as well. And now let's start with quantization of a single variable. We're going to look at both 4-bit and 8-bit quantization, which we saw in the lecture notes, are different amounts of compute space that we allow to store our numbers to a particular precision. We're going to be storing these as 4-bit and 8-bit integers. And so let's have a look at how we do that for a single value. We'll define two functions, one to quantize a value and another one to unquantize it. What we're doing when we quantize a value is putting it into a set of discrete chunks. We're also keeping track of the value that we used to reduce the value into these chunks so that we can also extrapolate back into the more refined value that it started with. However, as you'll see, doing this process introduces some losses in accuracy, and we'll see exactly how that plays out. To start with, let's look at the quantize function. So we have our definition quantize, and we'll be quantizing a floating point number to an integer. Since any number that's larger than 1 on the left-hand side of the decimal can be represented as an integer itself, we actually only need to worry about values that are between -1 and +1. And so the range for this quantize function will be for all values between -1 and +1. It'll take in the value that we want to quantize and also the number of bits that we are going to select to use for the quantization. So this will typically be 4-bit or 8-bit. It'll return the quantized value, and we'll also make sure that we're checking that we're only going to quantize values between -1 and +1. All that's required to quantize the value is to take the value that we input to the function and then multiply it by 2 to the power of the number of bits minus 1, and then subtract 1 from that value. We then round that to the largest value, and you could also do different schemes depending on how you want to quantize it. We're going to use the fairly standard approach here where we multiply a value by this 2 to the power of the number of bits minus 1 to get our quantized value. Once we've quantized our number, we'll also need to unquantize it. We unquantize the value by taking the quantized value and the bits that it was quantized with. That's going to be quite important. You can see here we'll take the integer back to a floating point number given the original number of bits. You can't mix and match the different types of bits as you'll introduce more and more errors into your process, and there's already errors associated with quantization to start with. To dequantize or unquantize your value, you basically undo the process we did before where we multiplied by 2 to the power of the number of bits minus 1. Here we're dividing by 2 to the power of bits minus 1. Let's set up this definition and see what this looks like in practice. We'll test this for both 4 and 8-bit quantization, and we'll use the value of 0.5. If you think about the value 2 to the power of bits minus 1, for 2 to the power of 4, we'll get a particular maximum and minimum range, and for 2 to the power of 8, we'll also have that same range. We can test this by looking at different values of the variable value and looking at how the quantization treats the extremes of those values. Let's start by quantizing 0.5 with 4-bit and with 8-bit encoding. when we run this cell, we can see that with our original value of 0.5, the quantized version becomes 4, and the unquantized version becomes 0.57. For 8-bit encoding, we see the quantization value be 64, and the unquantized version be 0.503. So you can see we've already introduced some error looking at 4-bit quantization and 8-bit quantization. And that's because we're only allocating a smaller amount of memory to represent the value that we're looking at. Let's take this value up to 0.99 to see what would happen at the maximum value of our range. You can see the 4-bit quantization maxes out at 7, and the 8-bit quantization maxes out at 126. When we think about what 2 to the power of 4 would be, we would get something like 64. However, we're doing 2 to the power of bits minus 1, and so 2 to the power of 3 is 8. And so the maximum value that you could think of that we would get here would be 8. So if we put in 1.0, you can see we saturated that value because we also have this minus 1 over here. So that means the largest value on the positive side of quantization is 7. And if we were to change this to minus 1, you can see we would get negative 7. Likewise for 8-bit encoding or quantization, 2 to the power of 8 or 2 to the power of 7 being 128 gives us the range of values that it can output. If we pick the value of 0, we actually get lucky in that 0 has a very special value in the quantization scheme, and so we actually get perfect retention for the value 0. If we return back to 0.5, we get these results back as we did before. So now these quantized functions are working as we'd expect for a single value. Let's look at how we might quantize a function. The quantization of a function relies on the fact that we're actually going to sample a continuous function at discrete points. This is true no matter how precise our compute is, as every function that we can actually calculate has to be calculated at a finite precision, even though it might be at double precision or even more than that to give the appearance of continuous function values. In computers, we obviously have to store these values as finite numbers. This means that we can quantize any function that we can represent in our computers. We're going to take a sine function as an example of quantization, and then we'll generate the quantization of this using the functions that we've just defined above. So we'll create a linear space using NumPy from -1 to 1 using 100 points, and then we'll calculate what the value is using the sine function for each of those points. We're then going to quantize all of the values of y for both 4-bit and 8-bit quantization and store that in an array. We can then look at what the loss would be over the average, so the mean loss for each of these different approaches, and let's see how well it can quantize these functions. You can see that for the 4-bit quantization, we get an error down to the 3rd decimal place, and for 8-bit quantization, we're down to the power of -6. So we can see here that 8-bit quantization performs much better than 4-bit quantization, which is also intuitive. So let's look at what the consequence actually is of doing this sort of quantization and what we're losing when we quantize to 8-bit and what we lose when we quantize to 4-bit. We're going to plot the original function. We're then going to plot the quantized versions of 4-bit and 8-bit, and then we'll also plot what it looks like when we unquantize those functions. So we can see our original plot here is nice and smooth and is given to the precision of the machine that we're working with. We can see that because we're dealing with a unit sine function, it oscillates from 0 to -1 to +1 and then back to 0. For the 4-bit quantized version, we can see the distinct chunks of values from 0 down to -7, up to -7, up to +7, and then down to 0 again. This represents exactly what we were looking at in the testing of the function before, when we put in different values between -1 and 1. The scaling value here that you see between 0 and 7 is how it represents values between 0 and +1 using integers. It then takes that factor and will scale it back down to any value between 0 and 1, and likewise from 0 to -1. Let's look at the 8-bit quantization. You can see that even though we use the same number of points, they're not clumped together in the same way that they are for 4-bit quantization. Instead, we get a much smoother representation, and you can also see that we're storing much larger scale numbers on the y-axis here as well. When we unquantize these functions and put them through that reverse process, you can see here that the 8-bit quantization preserves far better the structure of the sine function than the 4-bit quantization does. And you see this as well in the approaches in large language models, where we use typically 8-bit encoding as standard rather than anything more than that, although further development into quantization of less than 8 bits is currently underway, and we're seeing some impressive results with that as well. Typically, numbers are stored at 32-bit floats, and so we're already at 25% savings with 8-bit quantization, but we could halve that if we can improve our 4-bit quantization schemes as well. Now let's look at how we can quantize a simple neural network. We're going to be using some special functions from PyTorch, but under the hood, they more or less perform the same functionalities that we've been doing up until now. When we define our neural network, like we've seen in the course so far, we use a specific structure in PyTorch to define the structure of our neural network, with both the class definition under the init definition, and then also a forward pass definition for our neural network. We're going to be using stub locations for where we will quantize and dequantize the values as we move through the architecture. When we get to training and the actual quantization procedures, that's where these stubs are actually replaced by the operations that PyTorch will perform automatically for us. You can learn more about this by checking out the documentation at the PyTorch organization documents. Let's define our simple neural network architecture. You can see in the cell here, we are defining our net for our neural network. We start with a quantization stub, which you can see here will act as a placeholder. We then have 2 linear layers. We're going to be assuming that this will be a flattened MNIST neural network. And so the MNIST images are 28 by 28 images. And so we're flattening these as 28 by 28 cells. And then we have 10 classes for the MNIST characters from 0 to 9. And so we have 2 neural network fully connected layers. At the end of our neural network, we also have a dequantization stub as well. And then in our forward definition, you can see here we're just piecing all of this together. So we take in our input, we first pass it through the quantization. We'll then have our activation and fully connected layers connected to each other, and then we'll dequantize our values at the end. Now we can download our MNIST dataset from the Torch Vision datasets, and we're going to store that to our working directory. And then we'll define our cross entropy loss function and a stochastic gradient descent simple optimizer. This will take just a moment to download. And now we can train our network. We're going to train the network without doing any quantization. This is going to be full precision training, and then we'll quantize later. For now though, we'll just loop through a fairly standard training of a simple neural network to complete the MNIST challenge. This will just take a moment. Our training is now finished, and now we can move on with our fully trained neural network at full precision. We can look at how we can quantize this now that it's finished. It's a fairly simple process to quantize our model using PyTorch. We use the we will first get some default configurations using quantization. We'll then use our preparation in the quantization to prepare our network, and then we'll finally convert the network to our quantized state. Again, check out the PyTorch documentation if you're interested on the specifics of how you would do this, but we're more or less just using the defaults here. And now what we can do is we can save the original full precision model, and we will also save the quantized neural network to disk, and we can look at exactly how much we save by quantizing our model. As you can see here, we have 408 bytes for the original model, and 408,000 bytes for the original model, and 108,000 bytes for the quantized model. So you can see that the quantized model is nearly a quarter the size of the original model, which makes sense given that we're going from 32-bit representation down to 8-bit for much of the model. There are some pieces of the model that weren't quantized, but the largest component inside the model are the neural network layers, and those are what are quantized. We can take a look at the different parameters inside the model to see how they compare between the original and the quantized model. We can see our fully connected weights here in the original model and the biases in full float precision. And we can also have a look at the quantized layers as well for the quantized neural network. And you can see that these have some slightly different values and some different layers. We can read a little bit more about the quantized versus non-quantized. You have the quantization scheme that was used. You can have the type of value that you have here. And so you can see here we have the torch quantized integer 8-bit, which is the default for PyTorch. And you can also see that there are some parameters for the quantization process that are specific to this particular quantized model. Again, you can read more in the documentation about the specifics here, but the defaults work very well. We can also look at the output of the original and the quantized model if we pass through some kind of random input. And so this is using the original and the quantized neural networks at inference time. So at training time, we had to train the model with full precision, but we can actually use the quantized model if we want to at inference time. Now you can see here that the output from the model is at full precision, and so we have our decimal representation, but you can also see that apart from one value in the output of the quantized model, everything else is set to 0, and that's to do with the precision that we gave the particular model. It's unable to see any of the other values apart from 1. We can run this again to see if we get a different result as we're doing different randomized inputs. But you can see here that due to this scheme that we had, these inputs are not picked up as different for the quantized model. And so this is a risk, or this is a cost that you have to keep in mind when you work with quantized models. Their performance is degraded compared to the full precision model. We can look at the error present in this model, and you can see that the quantization error is indeed quite large. Just to check that we are indeed looking at different types of weights for our model, we can see that the original model is comprised of 4-byte representations for the fully connected weights, and the quantized model has just a single byte for their weights. And so in this example, we're showing how you can quantize different neural networks, not just large language models, but indeed large language models use this very heavily as there is many billions of parameters. And so the amount of savings that you could have by taking just a quarter of the precision there is dramatic. You don't need to go to 4-bit quantization necessarily. 8-bit quantization is still a huge amount of savings, and more refinement to these quantization schemes keep coming, which improves the performance and the accuracy of these models. Hopefully this has given you a good sense of how quantization works and demystified it a little bit so that you can use these in practice with the right knowledge of the cost that you pay when you do quantize.